Hello everyone. Thank you for joining IFAS AI and Data Science Seminar Series today. We have two excellent speakers for their sharing their presentation. Our first speaker is Dr. Rafael Muñoz-Carpena. He's a full professor of hydrology at University of Florida. His work focuses on integrated environmental systems modeling, including interactions between hydrological, ecological, and human components, and global sensitivity and uncertainty analysis of this integrated system. He's an elected fellow of American Association for the Advancement of Science, American Association of Agriculture and Biological Engineering, foreign members of Royal Academy of Engineering of Spain, and he has received numerous prestigious awards such as ASAB John Deere Gold Medal in 2022. His presentation is about convergence of mechanistic modeling and artificial intelligence in hydrologic science and engineering, and lessons for other fields.
Okay. Good afternoon, everyone. Can you hear me?
Yes, we can.
Yes. Okay, perfect. So I'd like to, let me put this up on the screen. I'd like to recognize my co-authors, of which one of them happens to be the second speaker today, Ziwen, who also collaborated on this project, and former PhD student of mine, Alvaro, and also Gary Fox from North Carolina State University, and Oki Baitland from Flinders University in Australia. The work is published just recently on PLOS Water. I put the reference there if you want to look at more details. I'm just going to do an overview of what's in the paper, hopefully to provoke a little bit of thinking about what is the right fit of these technologies that we have right now in the context of some systems, particularly in this case, I'm focusing on water, but I believe that some of the take-homes could also be applied to many other different disciplines. Okay, so let me get started by speaking about the discipline, but I'm sure this can resonate on other of your disciplines. We have on one side, of course, the focus of hydrology is water, okay? And we understand that water, because of the nature of water and the interactions with the natural environment, water flows through very dissimilar and heterogeneous and isotropic materials, and therefore there is an intrinsic spatial and temporal variability in the flow of water and substances that go with the water. And then along the path, there are many distinct biogeochemical and human interactions that also affect the water often in many unknown ways. So the hydrology as a science, which essentially would be everything related to water, so it's a very broad definition, matured in the 19th century and early 20th century, mostly as a mechanistic, physics-based application of first principles, conservation of mass, energy, momentum. And then in time, it expanded to incorporate other aspects related to water at the interface of from physics to chemistry, biology, and more recently, of course, the human actors, which of course, in the context of what we now call the Anthropocene, they are integral components of the dynamics of all these systems. So the establishment of the discipline benefited in the middle of the 20th century with the beginning of computers and mechanistic simulation models. And I should mention that what is thought to be the first mainframe application of computers was actually around the Stanford watershed model, which was a hydrological model, okay? And it was the first time that, a large by the standards of the time, you can imagine that wouldn't be the case today, but it was the first application in computers. So computers, physical principles, mechanistic understanding is an integral part of the discipline. And then, but we understand also that to ground the understanding of water, we need to have measurements. And in fact, measurements have been from very early times. We have ancient records of rainfall, systematic records of rainfall in India before 400 years before Christ. There is a systematic experimentation, for example, the distribution of velocity in rivers by Leonardo da Vinci in the 15th century. And all this, in essence, the development of the more mechanistic physical understanding was grounded on measurements. But even elegant theories, physical, mathematical theories, face uncertainty when in their application to these uncertain domains or variable domains that water usually goes through. So we, from the beginning of the disciplines, we understand that what we could predict very closely under controlled conditions, when we go out in the environment, actually is much more difficult, okay, because of all these uncertainties built into the system. So in addition to variability, we also are facing, as we all understand, non-stationary conditions, meaning that there are important changes introduced by both land use, climate changes, which essentially complicate our understanding of water as a system that interfaces with these other systems, because with one important difficulty, which is that the past is no longer like the future, and therefore our observations need to be corrected also looking at the future. So an additional layer of uncertainty on top of everything else. So this essentially motivates that from the very beginning, statistics, the handling of data, the understanding of these uncertainties, how to propagate them through the system, and ultimately assessing the prediction uncertainty of these approaches was integral to the development of hydrology as a science. So in this map, for example, in this time line, we can see on the left hydrological cycle with many important contributions from just the last 40-some years. A lot of equations, computer models, principles were derived, accelerated by computers and other inventions from 1930, in this case, to 1980. And then in parallel, you can see the developments of statistics and also technology observations and such. And what I have to mention here is that a number of the concepts that were developed in general statistics actually were developed in the context of hydrological data as well. Gumbel distributions, extreme values, these kinds of things that are used also in other fields were developed in the context of hydrological data. So as a discipline, we are not ignorant of statistical advances. And in that context, the new approaches, the artificial intelligence, machine learning approaches, are then in the context of other statistical tools that could be used, okay? And we realize that, of course, they offer a great predictive performance for direct applications on uncertain processes. But when we, in fact, the main objective is prediction and not necessarily understanding of what is driving that response, what we often refer to as a black box approach. Particularly when we go into deep learning, but also machine learning methods, and many of these, they are becoming very useful and interesting tools to essentially apply them to understand or learn from spatial and temporal patterns, okay? And it's already making a strong impact on hydrological modeling and understanding in hydrology. So, however, looking at, and the paper contains many references, to studies up to this point, we find that often many papers essentially, the main approach that they present is that I can do this with artificial intelligence or machine learning, but they do not explicitly pose the important hydrological questions, the advancement from those questions that could be introduced by the application of this tool as any of other tools that we have available to us. So they lack comparison with benchmark approaches, which are already widely used in the field in terms of other models and other tools, other analysis, including statistical as well. And instead, often it's just, this is the new machine learning algorithm or artificial intelligence, and then we are going to improve the predictions in this much. But given that we are not understanding the processes, the question is just that single-minded prediction focus without understanding systems understanding, or even comparison with established technologies, if that is really sufficient or is informative, okay? So let me, some of you might know this famous Gardner height curve. So essentially, this is the new technology adoption curve. And of course, everything starts here on the left-hand side. Time is on the x-axis. Y is some measure of use or visibility or expectations, okay? And then the technology trigger, the new technology comes into the, becomes known, and then people start getting enthusiastic about the new technology. And then it keeps rising, the adoption, the expectations keep rising until this maximum point that is often called the hype or inflated expectations. And in fact, this is also called Gartner's hype curve because of that. But soon after, or maybe not so soon, but along that path, there is a failure of the technology. There is a particular application or applications where it doesn't really perform at the level that was expected. And then these visibility expectations fall into what is called the trough of disillusionment. Oh, it doesn't work. It's all news. We don't want to spend any time there. The funding gets cut out, on these things. And then eventually, after this period of disillusionment, somebody comes back and says, well, it's not what it intended to be or was thought to be, but you know what? It's actually quite useful in what we call the alignment process, the alignment period, and ultimately production phase. Okay, so this is a very typical for many examples of new technology adoption. And then what we did is we went back and we said, well, and how about use of artificial intelligence, machine learning, hydrology? Can we map this hype curve? And then what we found is that if we do, and this is based on a Mendeley search of publications related to machine learning water, AI water, or both and water, and then what we found is that there is, in fact, this period of inflated expectations happening. Now, will it crash at some point? Okay, so will this hype stay, or rather will follow the more classical Gartner hype curve? But we already have some warnings here. You probably saw this article on the New York Times. AI poses risk of extinction, industry leaders warn. We know that there are already big impacts of this technology that are not meeting expectations and rather are being negative, at the society level and on particular applications. So following that, it's expected that there will be this phase, okay, the trough of disillusionment, following the alignment and production. And I think our goal as scientists, engineers, is to essentially move beyond these intermediate phases of hype and disillusionment and envision what might be the production phase. How will this new technology fit within the existing tools that we already have at our disposal? What are the advantages, disadvantages, and such? So one thing before I go into more, describing this a little bit more in detail, I want to also throw a wrench into all this process, because we need to realize that if the over-reliance on data is perilous, is very dangerous, okay, and could also lead to unintended results. So in here on this graph, I'm going to represent on the y-axis the fraction of the system variance explained, which essentially is how much do we know about the system, okay? And the scale is from 0 to 1. 1 is represents I have a full understanding of the system that I'm interested on. 0 is I don't have any understanding, okay? And then so let's go step by step. Now this is the real world. The real world, by definition, contains all that variance, those dynamics, those processes, and therefore is self-entailed, or basically on its own, it has all those relationships and information. And now let's go one more step, and then let's take data. And we know that data is opportunistic, is here, now, okay? And that also is limited by necessity. So there are a number of behaviors in the system that likely will not capture with our limited data sets, but they're still part of the real world. So this is what we start with when we take a data-driven approach, strictly the amount of information that we have, and we already know that we are losing information in this first step. Now, let's then take this further into an abstraction of the data, and from there, we fall into what we call abstraction, structural error. And in the context of machine learning and artificial intelligence, is the selection of what are the variables, the features, whatever it is that we are building into this, that's subject to some conceptual model, some simplification. And then our ability to describe what is on data then gets reduced by whatever we are leaving behind. So we're going down into what fraction of the real system we can actually predict. And then finally, the model application with the parametric uncertainties or the particular uncertainties for the that application, they carry on into further degradation of what we can really resolve. So that we refer typically to calibration error. And then finally, the loss of information that we can get in a good day with respect of the data is about what I'm showing in the slide, and probably optimistic at that, And so it begs the question, what can we really see at the end of the day? And I know that the paradigm of machine learning is that, or artificial intelligence, we have the data, and then we're going to build this response because we know the data. Well, the problem is, as we can see here, is that the data is not really telling you everything. The model doesn't tell you everything that is on the data, and so on with the application. So at the end of the day, we need to be very careful that what we are using really responses to our expectations on how the system is really responding. There is one more point that I want to make with this slide, which is the difference between interpolation and extrapolation, which is a very key concept in statistics, as we all know, where in statistics, in classic statisticals, we typically, or we must stay within the domain of the data that we train the statistical tool for. So we can interpolate within, but we could not extrapolate because there is no assurance that the model is going to behave as expected outside the data range, okay? This is important to remember because extrapolating from machine learning, unless there is additional evidence for that extrapolation, is not really a good idea, okay? So with those concepts in mind, the motivating questions is, what are the advantages of this new AI technology compared to existing other mechanistic and statistical tools? This could be, again, a relevant question for any of the fields, any other fields. What are the limitations? When to choose the AI, ML approaches over the mechanistic or other established methods, including statistical ones for the same problem? What are the uncertainties associated with these methods? How do we deal with them? So what we did in the particular field that we described is we separated, we did sort of a mapping of based on spatial and temporal scales, which are important in the field of hydrology to describe processes at different scales. And then we just put x-axis for the time, y-axis for the scale, and then we created 4 quadrants, arbitrary as it is, where we went from a very fine resolution, very rapid processes to very long processes, lowercase t to capital T on the x-axis, and the y-axis from the point scale all the way up to global scales, watershed, regional, other scales in between. And then we started looking at what might be the characteristics of these problems so that we could evaluate them with respect to what tools there are there, how does AI or ML approaches could fit within these, and then what we could learn in terms of new or existing applications which are very useful of AI ML in this context, and others that we could envision happening, following. So we have in the left hand side, we have these early warning systems, or essentially problems which are short term, smaller scale, where we're interested in predicting, extremes or some quick behavior which is of importance for whatever system we are is linked with the water. Okay. And then we went through every one of them and sort of classified what are the existing tools, what might be the challenge related to, for example, do we have enough data at the scales that we are interested at the fine resolution, issues of temporal autocorrelation, how do we resolve those, nonlinear processes, multi-domain physics at those scales, things like that we might not be right now in a good position to answer yet. And then other tools that we are already using, including AI, ML, you can see there. And then we did this through every one of these quadrants, or types of problems. For example, in this one is going into the larger scales, but sort of the middle type of temporal predictions. Then on this one, we went for the long-term kind of predictions, okay? And then finally, on this one, we were on an intermediate temporal scale with a smaller spatial scales, other types of problems, and other issues. To summarize all these without going into details, again, that's you can consult the paper on some of the details, but we found that the challenges in general terms of the different types of problems were that on the type 1 problems, and again, those are the problems that are dominated by a small or intermediate spatial scales, but small temporal scales. This multi-domain, multi-physics problem, was a big challenge in terms of understanding or advancing the systems, the knowledge on these systems. On type 2, the interpretability, explainability, and we are talking now about the intermediate temporal scales, but large spatial scales, and then high feature uncertainty on the longer scales and robustness of these scenarios and ensembles, data scarcity and scale matching for transdisciplinary approaches on this final one, which was, again, within the intermediate temporal scales and small spatial scales. And from there, what we identified as potential vision on where machine learning can be important to advance our current knowledge and understanding from the systems level. On the data, we divide into 3 main areas: data management, insights and knowledge extraction, and then the structure of modeling itself. How can both the artificial intelligence and machine learning support or produce synergistic effects, improvements with respect to the current approaches, which are more mechanistic based, okay? And so for big data, we know that data management is becoming a big challenge. We have lots and lots of new data streams particularly from IoT, the Internet of Things type of technologies, cloud technologies, large storage space. And perhaps we are falling under the curse of, more data, is better. Maybe more data is not better, because now we have to wade through that data. So the artificial intelligence, machine learning, data analysis is becoming indispensable to wade through that data and obtain new insights on the data that can allow us to advance knowledge or prediction tools along the way. But how do we put together all this data is a big issue, okay? I mean, data harmonization has been at the core of the big challenges of many disciplines, and perhaps we are looking at a new world where we might not be obsessed so much about that, but perhaps the artificial intelligence interface, based on the query that you pose, will be able to collate the data from a distributed environment where the data resides without having to do this extra effort, which is often, impossible to collect all the data in a single repository with common standards. Instead, we can probably fill gaps with secondary information from other sources, tailor the data and represent it to the particular application, and therefore helps us into this massive undertaking of using the amounts of data that are available to us. For this, we're going to have to decide novel QA/QC standards that are aligned with this type of data engines. We are going to have to also develop ways to access these new tools through APIs, interfaces that are able to, in a more general way, get us to the endpoint, which is getting access to that disparate data at multiple resolutions, temporal scales. Insights in the knowledge extraction is a very exciting development, because we have the opportunity now to formally incorporate knowledge that was not really well represented on most of the analysis we do, which is what we call, general terms, we call the normal data that we use, numerical data, we call structured data. These are structured data sources, which are, they reside on images, reside on sound recordings, on newspapers, things like that. It's very hard to really elevate to a point that can be used. But there are big developments, natural language processing, knowledge engines, all these things are coming to place where we can combine this type of data, we can encode that information, and then also leverage that information along with existing data. And it becomes particularly exciting because we need to remember that we have other types of sensors in the landscape, which are people. They have been there. They are there. They have an understanding of how systems work, and also they have been faced with many often with extremes. And they have responded to those extremes. They have adapted, they have mitigated those. And there is a lot that we can learn from incorporating this into the other principles that we are already using here. And for that, AI and artificial intelligence and machine learning are critical components to that. I don't want to extend too much on this. I will jump into in a structure of modeling, which is the other area. There is a tendency to start thinking about, now we can put together all layers of models representing all these interconnected systems that I mentioned before, all the way down from the physical up to the human system. And then I can create these big, large, what they are called big models or stack models that could potentially mine through and give us these responses. But the fallacy of that is that what are the pieces, the details? What are the pieces? How are they connected? Do we really understand the individual components? And ultimately, altogether, can we really trust what we are getting out of that? And there is a lot of reflection on what the opportunities are. The cost is huge. We are moving into that space also in academia. It was previously taken by large companies, okay? And but there are other opportunities within that where AI, in addition to building these models and the connectors between the models and some of these components that we don't know well, okay, there is also the opportunity to simplify or create emulators or meta models, basically of the very large and complicated tools that we develop. Can we simplify them for specific applications based on the important components through some sort of emulator, which is based on a learning object from artificial intelligence and machine learning, okay? Ultimately, parsimony, or the idea of having a few important processes as opposed to everything under the sun, is quite important for not only understanding theoretical concepts, but also management, particularly management objective applications, okay? So the ongoing developments and applications support that machine learning could be a very powerful inductive and exploratory tool to develop new theories and address standing gaps in hydrological data management, modeling structure, knowledge structure in complex changing systems. And I think this is also true for many other disciplines. Just one more minute to finish here, but I want to throw in also what we are seeing, this widening gap between the have and have-nots through the introduction of these technologies. This week, there was an interesting workshop on rural AI, essentially looking at what is the space of artificial intelligence within the rural areas and what are the differences that the different application of these technologies could be start moving on. This is an analysis that was done last year on what are the applications that are now being done on machine learning. And you can see clearly the regions, okay? You have the global north with 80% of these applications and the potential benefits that they imply. And then the south, the global south, which is not accessing these opportunities clearly, okay? In addition to that, the access, okay, there is also the issue of ethics, okay, as well as equity on access for the different communities that this is served. And this was, as I said, discussed this week. It was very interesting conversation. Now, finally, I want to just say that learning is only one part of what originally, when McCarthy in 1955 defined artificial intelligence as the science and engineering of making intelligent machines, learning is only one component of the whole, what we call the AI hat, or essentially this house where you have the roof and you have the floor, and every part of that is part of the hat or the house. Okay, so you have just learning from sensonics, big data, the patterns, the prediction, all these things are critically important. That's where we have advanced very fast. There are also, of course, a lot of efforts on autonomous machines that can incorporate this knowledge, but the intermediate, the connection between what is learned and actionable information that can be deployed in machines, this decision analytics is probably not as developed as the other branches. So therefore, we should take a balanced approach across these three domains to run them in parallel so that we can ultimately achieve the utility, the final application of these artificial intelligence and machine ideas, okay? So the take-home message is that artificial and machine learning expertise is critical to the discipline. There are exciting opportunities on this and other disciplines that artificial intelligence machine learning needs to become one more of the standard tools in our tool chest, but also in others, and not just replace the others, but also how does it combine with the others. Our graduates at the university must be able to analyze ever larger amounts of data and interpret these to extract new systems knowledge, not just predict, okay? And this requires that the analysis is grounded on solid understanding of mechanistic principles and concepts, and not just the prediction. Critical thinking and limitations like the over-reliance on data must be clearly stated and understood in all the applications, and scientific papers applying the machine methods not just to hydrological research but across other disciplines should address why it's important and more suitable than other conventional mechanistic or even statistical approaches that are used in the discipline. Also, these implications on equity and ethics components are forefront and should be considered from the get-go in development, design, development, application of these, okay? And ultimately, as the AI solutions take a bigger decision, a bigger role in decision-making in high-stake problems, we call for the creation of teams that can actually address all these components that I have described, including the ethical, the social components, while we are in the design phase, as opposed to as an afterthought or as a later on trying to fix the problems that we can create with this technology. In the end, we are faced with the reality that AI-based products and machines do not think like humans or are subject to human and ethical restraints, and we might not be able to fully explain the raw predictions made by them. Thank you.
Thank you very much. Is there any questions from audience?
I do have
Charlie?
a lot of
Oh, Henry.
questions,
Oh, okay, Henry.
I don't think we have time for it. It was a very, how can I say, deep talk. Thank you, Rafa. I think there are lots of philosophical questions to be asked about that. Very interesting. But for the sake of time, maybe we'll do that next time we go out for coffee.
Absolutely. Thank you, Randy.
Okay. Maybe we can ask one question. Charlie, do you have question or?
Maybe a short question. Yeah, this is a very thought-provoking talk. So, Rafa, you mentioned the combination of AI and mechanistic models. So, in your opinion, what's the kind of approach and the framework to combine these two together?
Yeah, I think, as I mentioned, the dimension reduction approach that you can obtain from AI and machine learning on systems is very interesting. In other words, you can, starting from data and combining these methods with techniques like factor importance analysis of different flavors, even more sophisticated than the typically ones that are embedded into the existing methods, which account not only for direct effects, but also interactions, clearly. But once you go through that process, you can identify which factors are the critical ones for the particular system and application that you have, which then can lend itself to develop models, gray box or white box models that can then be used and tested against the original just data-driven approaches. And in the formulation of those models then is where the learning process, the advancement of knowledge goes into place. So we published recently a paper where we took a look at a very uncertain and difficult problem to predict. We spend a lot of time, as you all do, putting together data that could be representative of that problem across many different domains. And then we went on and applied first as a dimension reduction technique, machine learning. Then we went on and did this importance analysis. And then we identified the factors. And then we were able to construct, it was first a statistical model that based on just only the important factors identified and the form of action of those factors in the outcome or the output of the model. And that was a step into creating a predictive equation that was, you could read, it had terms, with certain relationships that can lead us into understanding more in depth what are really the key drivers for that uncertain process that we didn't know earlier. Okay.
Thank you, Rafa.
Thank you.
Okay, great. Thank you so much. It was a really excellent presentation. Now we're moving on to our second presenter, Dr. Ziwen Yu. He's an assistant professor in agriculture and biological engineering department at University of Florida. His research. His research focuses on data-driven knowledge generation, emphasizing data management, pattern recognition, predictive analysis, and knowledge extraction. His current research explores ethical implication of data in agricultural and urban natural resources management, and he's interested in legal aspect of data technology applications and their role in shaping various industry, particularly agriculture, and addressing social inequality within AI ecosystem. The title of his talk is Data Ethics in AI Development in Agriculture.
Okay, thank you, Dana. Sharing my screen here. Okay, can everyone see my screen?
Yes, we can.
Yes.
All right. Awesome. So thank you for the invitation to be here and giving my my presentation regarding the topic of data ethics in AI development and implementation in agriculture. So I think the topic here is kind of a little bit scale up from what Rafa mentioned regarding AI in hydrology. And in agriculture, I think hydrology is an important part for it, but we also have these implication and application in other fields. So I'm trying to generalize all these applications and see how the ethics regarding data that has been represented and can be inferred from the current status. Okay, so just trying to give an overview of my presentation here. So firstly, I'm gonna talking about the change of roles of different stakeholders in agriculture on the AI. And then there are a couple aspects of data ethics in agriculture I'm gonna cover. One is from the legal side. So what is the data rights and obligations? And then, so once we have data for the modelings, what is the quality of the data that's gonna impact the downstream modeling and how we're gonna working with it. And then after we using the data to do all these modeling and get to some results, how are we going to productize these results, and what is the security and traceability that is so important to be considered for further marketing and economic consideration. And then finally, I'm going to talk about the future plan regarding these future developments. All right, so firstly, how data rights and obligations that has been changed, that is so important under the change of AI that has been put on these stakeholders' roles. So traditionally in agriculture, all these technology innovation has been driven by the technology providers or the companies who doing this kind of research. And then farmers are purely a customer who just adopting and purchasing these services from these technology providers. However, as AI is joined in, an AI model cannot be produced without the data that it can be learned, the information or the knowledge from. But these data is actually coming from every farm. So basically nowadays with AI, farmers are not just a adopter or customer for the technology. They are also a contributor who is providing the data and providing the knowledge that has been used for AI training and technology development. So that's the big difference in here. It's from a chain shape to a closed loop between companies and the farmers. So and also once the data is coming to these innovation process, the product of data can also be considered as an additional branch of this value chain that can be used as a new type of commodity, which also can be traded financially in a different scale of market and bring new income to farmers. So you can see that all these entities and all stakeholders are chained together, not in the one direction, but interactively connect with each other. And all these connections are built on data. So the next question is, who owns this data, as data is so important and plays and changes the whole world in agriculture. So from some review that we have done on the legal side is the industrial practices right now between the companies are using these agreements that they made, which is unbinding. There are two types of main agreements that we can find in the world is so in EU, there's a code of conduct that has been passed in 2018, confirm farmers' rights to own these farm data. And then in US, there's a company called Ag Data Transparency, which is established in 2014. They published these 20 principles that companies can obey, and the fundamental rule is farmers or data provider owns the data rights. However, these agreements are both non-binding. So even though companies may agree with it, they still were not getting any legal enforcement if they violate. So how is the legal enforcement, or how the legislation specification of it? We dug into the copyright law and found that it's not easy to find a perfect fit on it. And the only option that we can see from the current legislation specification is trade secret coupled with contract overrides may be the option, but there are multiple conditions that is very tricky to obey and to be represented. So how tricky? Here's an example that we found from a giant company in the agriculture industry. And then they have these the contract terms or user's manual conditions. So basically, we're trying to think if data can be treated as trade secrets. And then there are two important components. One is it has to be represented as economic values. And two is the disclosure of these trade secrets has to be controlled. So if you can imagine that data is transferred from farmer to a company called XYZ, then here's the term that we quoted, right? So I'll highlight the pieces in here is, in here, you agree, you as farmers, you agree that XYZ may use, display, perform, produce, modify, and distribute such data, which means farmers relinquish their rights of the control of this data, and then without any compensation paid to you. That means all these transactions, the data from farmers to the company does not represent any economic value. So in that case, this data is not a trade secret that is owned by the farmers. We're not sure this term is going to be also the same. One company gave the data to another company, but at least at this stage, farmers are not owner of this trade secret. So how farmers thinking about this? We did a survey in Florida in last year and trying to know how these perceptions by farmers. And then we think education distribution is a very critical component in here. And there are two critical questions that we asked in the survey. One is, have farmers ever learned about data ownership? And are they familiar with the data obligation terms in their contracts? And you can see that in here, for the ones that whose educational level is lower than or equal to undergraduate level, most of them are not aware of data ownership, and they are also not quite familiar with the data obligation terms in their contracts. And this ratio is quite different from the ones that has education level that is greater than graduate level. So almost half of them are familiar with no data rights, data ownership, and also familiar with the data obligation terms in their contracts. So in this case, we can see that this very discrepancies in the knowledge among farmers that are subject to the education level. And then, so how our education and how we can help them to leverage and to mitigate this gap is a very critical one. Otherwise, it's very hard for us to, distribute this knowledge to our audience, which is mainly farmers. And then we're also trying to see if, current language models like ChatGPT or natural language processing models can help us to, extract these terms from a contract and help the recognition and comprehension on. So just an example of how NLP model works. So if a text that has been, the company announced a partnership with a leading technology firm, then NLP model is basically extracted relationship between different entities in here. And basically the company and then leading technology firm are the two entities, and the relationship between them is a partnership with. So here's the development of NLP models. It was initially a rule-based model and then goes to supervised learning and joint inference. And then now there are transfer learning-based models. So the BERT, GPT, and Robota. These kind of models has been developed by Google, Facebook, and has they use Wikipedia and other these online language resource to train the basic knowledge for the model. And then I think everyone knows ChatGPT now, which is a large language model. So basically, we have used the traditional the transfer learning models, try to understand if these models can help to comprehend the relationship of the contract terms that we can find online. And actually, the result is pretty promising. So the general knowledge of a sentence that can be correctly, like 81% precision that can be obtained from the best model that we can train so far. But this is some expectation results and some the results that we get from language models. So basically, here's a example of terms, and what we're trying to extract is these information. So basically, the base knowledge. So you own quad water data, and then with different conditions that is highlighted in gray and green. So what we found is the NLP model, even though the ChatGPT can nicely recognize these main idea of a term. So basically, you own these data. However, what ChatGPT provide us is still, you know, a very general knowledge that it can recognize who owns the data, but it highlights that there are some conditions in the contract that is constrain all these ownership, but it cannot provide any detailed information of these conditions. And that is exactly that what we're trying to use these language models and trying to help farmers or customers to understand. So, so basically, we cannot get ChatGPT go any further to know these details. I think that's the direction that we're trying to go, and how we're gonna change the annotation of the data and how we fine-tune the model so that it can not only do the main idea of a sentence, but also focus on the conditions that is really related to the legal specification and all these rights and obligations from a contract. Then for ethics, another main topic is data quality. So in agriculture, we're using environmental data, which engage a lot of uncertainties from the ecosystem, environment system. Then data quality, outliers, missing data, and data drifting is something that we are suffering for any kind of AI models that we are doing. So here I just trying to introduce a data technology that I've been using to do the QQC model on a water resource project management. So we are monitoring soil moisture data, and then we encountered a lot of information that is unpredicted or not expected from our information, and trying to fine-tune this data and observe any abnormal patterns that we are not expected. So the technology that we're using is called a dynamic time warping. And basically, it compares the similarity of two time series patterns in here, and then we're trying to use rule-based learning to identify as the relationship between different rules that we can constrain and associate with two time series, and then to predict if there's any similarity predictions can be made. So here are some example we can get from it. The table just illustrates the green rules that we have combined in here, and then so the if you look at the right side, the green curve in here is a reference curve that we're trying to see if there is any similarity curves to it, and then any curves that is not similar to it. So what we found here is in the red curve, which is labeled as matched, to the reference curve is in a probability of, which is confidence value in here is 81%. And then the left value that highlights how this probability is higher than the average population data. So basically in here, if it's greater than 1, which means 81% is higher than the general population that using the entire data set. So then this example only gives us, you know, the orange curve is ambiguous, the red curves is matching. And then we tackle into another pattern, which is monotonously decrease trend. And we can see for this specific rule and the specific reference data, we can observe not only match and ambiguous, but also mismatch patterns, which is in blue. Then we're trying to improve make it more complicated. So we add more data sets. So previously we only used one single probes, and now we are introduce multiple probes. and then see if the same reference data with more data sets can provide more confidence and improve the results. So we can see here a previous ambiguous patterns can be recognized as this match pattern when multiple probe data is added in, which is increased accuracy for the data. And then additionally, when we prove that multiple data sets can improve the accuracy of this model, then if future or additional features is going to bring surprise to the model as well. And so in here, we're introducing the principal component to the patterns that we're using for referencing here, which is generally decreasing trend. And then if we introduce that features into our model with the same rules, then we can find that the previously recognized ambiguous and mismatch patterns has been grouped separately from the ones that is close to the match similarity. So then we can conclude that with a good features that selected by these rules, it can improve the accuracy of a model, and then helping us to detect these unexpected or abnormal patterns from the data. So here is how this model has been used in the real data. The upper left corner is the reference patterns that we're trying to recognize in a data set, and then green is the ones that is close to 100%, that is matching, and the other colors are represent to the ones that is with less confidence. All right, then, so as we are using data for developing or data modeling for AI, then how is the AI results is gonna produce? We call this data productization. And then what we are vision is gonna create an additional market for these products, and we call these products as digital commodity. So in agriculture, we try to know how these agricultural functionalities, especially for the social system, to the environment, to the ecosystem, to other entities. And then data and AI can provide us this capability to do this quantification. And especially I'm using ecosystem service for now. So carbon credits has been a good representative of these digital commodity, or DC, in this case, that account for atmospheric carbon sequestration. So it contributes to the climate change resilience to the whole globe. And then this product is actually completely driven from data. And then it is traded financially in the market as a commodity, which is, we call this DC, digital commodity. So here's the landscape of the carbon market right now in North America. And you can see that how many startups has been emerged in the market and how complex the system is, with different layers of functionality and different stakeholder, different rules, right? Then farmers are actually at a very fundamental level, only contacting with these project developers. And then they provide their data, these developers quantify the carbon credits and submit to the upper level for verification, for trading, and then for feedback from other things. So you can see that data is actually flow from farmers to all the different layers upper level, and how this data can be traced back, and how accurate this data can be maintained in such a complex system, even though it's in the very infant stage of this market. So those are something that is very critical to impact the whole development of the value that can be derived from data. And actually, the digital commodity is not just for agriculture. For other industry, there are different commodities emerged as already, but there are differences in here. So for agriculture, we have suppliers that farmers, and receiver are basically the industry companies who is producing these CO2 emissions. And so they just buy these credits to offset in their greenhouse gas emissions from farmers. And then the feature is, so farmers, they're relatively small, and then a lot of farmers are trying to engage into this market. But the companies who are doing this purchase are relatively large, and they're few. So comparing to other industries, it's reverse relationship. So the suppliers are relatively large, but few industrial companies, and consumers are smaller and many, which is the customers, the patients, the energy users. So it's kind of reverse structure as to the agricultural section. So here we're trying to illustrate the relationship in here. So for other industries, it's just one giant supplier and providing all these information or the data products to many small buyers. But in agriculture, it's the data has been supplied by these small suppliers. There are many small suppliers and turned into a single or just giant buyers. And then the buyers are actually buy these products from a very diverse structure. And the tricky part in here is it's a different supervision system. So from left side, a single company can control all his network. But on the right side, nobody is controlling this network. Suppliers or the small farmers, they don't have the technology, they don't have the resource, they don't have the power to do this supervision. And the buyers, they are not in the role that can provide supervision as they are buying stuff. So that's the big difference right now in the digital commodity markets. And what we're trying to propose is blockchain can potentially serve in these kind of markets based on how it's been developed to serve the data security, traceability. If we have blockchain as a single hub, that data has been collected from farmers, and then using the blockchain to go through other companies and other supervision entities that if we can introduce, such as USDA, such as DEP, DOE, and then that will be a alternative way that we can introduce supervision. We can provide data security and traceability capability to the whole market, and then to enhance the trust to the whole industry. All right, so here's the future plan I have in here. So I think a semantic data mining would be very promising in the future, especially so for the data ownership perspective. We can use this model to recognize data ownership terms in a contract. And also we can use the NLP to extract knowledge from the industrial practices and also some academia papers or textbook to build up all these knowledge graphs or network so that to enhance the learning experience. And then the next one is how there are going to be new ecosystems serving the data industry in agriculture. As data can be productized into a digital commodity, and it has to be supported by an ecosystem with the sustained data collection, with the trust building, with the traceability and data security. So all these are engaged to these ethical guidance and supervision. So these are some protocols that we definitely need to develop to guide the collection, sharing, and how these downstream developments and commercial activities should be regulated. And two is blockchain could be play a big role in this case, that as we see the market is growing, especially for the digital commodities, and then for different purpose as well. So if there's any violation for these regulations on supervision, then how are we going to trace back to these digital data activities in the market, and then to put legal enforcement onto these activities? Those are, I think, some very big potential that blockchain can play in agriculture for the future. Yeah, I think that's pretty much for my presentation here. And yeah, the time is perfect. All right, I'll be happy to take any question that you may have.
I have one question, Ziwen. So thank you for the great presentation. So I like the idea of using the a generative AI model to help farmer understand their ownership, the term in their contract agreement. Even though you showed the current generative AI model is not robust enough to continue give farmer the proposed suggestion, but I assume this can be solved if we train more and more data, more and more information. But if I think about this, I will think there will always be a risk that this model can make bias farmer make some a bad decision. So in this case, my question, if this happened, who will be responsible for this kind of the loss that biased by the model? Because if you want to promote this tools for the farmers, I think the farmer will ask this kind of question. I can try, right, but if there's something wrong, who will be responsible?
Right, that's a very risky question, and I didn't think think about that myself, and so basically, if just for example, we're talking about data ownership. That's a legal question that can be a big thing if we give very bad advice. It's not a like soil moisture or irrigation advice that is just changing a little bit of the yield. This is more like the rights and you know these even the civil rights to the farmers. So I don't have an answer for that, because even though the legislation system is kind of vague and need to be improved and give new specification on this topic. But what I'm thinking is the knowledge gap between farmers and these, even though we are the experts with different backgrounds. If we are getting to this topic of data rights in a contract, it's very hard for us to recognize these things as well. So I think as we are talking about these responsibility of laws, it's more important to how can we build up the gap, or to fill this gap of knowledge, that we can at least get some information, or at least identify the key parts in a contract for people to emphasize, to really get into, and they can interpret these terms themselves, but we just narrow down to the piece that they should focus on. So those are something that we think is the first step that should go through.
Okay.
Yeah.
Thank you. Yeah.
Is there other questions?
Isabel.
Yeah, thank you, Ziwen, for this wonderful talk. I like to ask about the question of in involuntary carbon markets, the principles of cost and demand and cost and benefits play a major role. Now, in this new system envisioned for using blockchain technology, the cost of collecting data related to carbon and carbon verification to assess carbon sequestration in a system, to, for example, translate them into carbon credits. How do you envision will that really bottleneck be addressed? Because cost play a major role to make these markets really work more efficiently than they have.
Yeah. So I would say there's definitely initial cost to the market and to every stakeholders in there to adopt this new technology. But the whole any kind of a data-driven commodities, or these digital commodities, it's a market is actually built on trust. So fundamentally, how these markets should be sustained is how we can build the trust of the market, or between the buyers and the suppliers. I recognize the cost that you mentioned, that is very hard for adoption for these things, but we just presenting a direction that we think at this point technology can help to build up this trust that is currently lacking in the market. And actually the market is relatively collapsing because of the lack of trust. So we're just trying to pioneer, if there's a data collection system. I mean, we have extension networks in here, so it's not fully used for data collection functionality at this point. And it's more because there's no market that directly needs these kind of service. And all the extension service for data collection is more on the research side and very isolated in different farms for farm service. But if there's a systematic need from a new market that can support extension service for data collection, and I have this blockchain sitting in the back to support all these reliability and traceability for the data collected from extension system, then that will be a kind of fundamental platform for the market can be built on. And it's not really for the carbon market alone. Any kind of an ecosystem service can also build on these kind of platform or data collection protocol. That's why at the end, for the future plan I mentioned in there is we can use, so the first step is we need to build a data collection and sharing protocol. And then blockchain is kind of a backbone of the technology support for these protocol. And in that way, all the trust can be built. So nobody is going to question, oh, the data is not correct, or the data product is not accurate or representative to the ground truth. We can, have the trust at the very beginning, and then the following development can be, fine-tuned, or we can tune the algorithm, we can tune the calculation. Then that will be, if there's any distrust concerns, it's more on the calculation process, not from data collection process. So I'm trying to think that for the current carbon market, it's more like nobody is trust the data collection piece, and everyone is, think it's a game. But if we can settle down and think data collection coupled with blockchain is trustable, then everything else is, it's kind of movement forward for the current situation. I don't know if I addressed your concern out there.
Henry, do you have question?
No, not right now. Thank you.
Okay. Yeah, I do have lots of questions about data collection, but I'll reserve that for later. Okay, thank you.
I always have a lot of questions, right? But now I think we're gonna take a good, very good,
Because of time. Yeah. Thank you for coming and also staying until the end of the seminar series. I appreciate it. Our next seminar will be November 17th. So I will send out the advertisement again. Thank you. Have a great weekend.
Thank you. Bye, guys.